Okay, now welcome back to lecture 14. So, today we'll continue the discussion on QED. So, what we stated was that QED is a theory of just electrons and photons. Okay, the only distinction between the case we consider with the scalars was that these are fermions. And analogous with the case with the fermions, I just wrote down what is the Lagrangian would be looking like. So let's do the same thing actually now here also. Okay, so let's write down LQD. QD. So the rule of the game is that it should be psi bar. Wherever there is a derivative, I should replace it by with del slash minus m psi minus 1 by 4 f mu nu f mu nu. Now let's go into this case in a little bit more detail actually. So this is invariant under a U1 gauge theory, invariant under local gauge transformations. So now how do I know that? Because I see a covariant derivative instead of a normal derivative, and so what's happening, psi bar is equal, psi goes to psi bar is equal to e power I theta of x q psi, exactly like the same way. And then psi bar goes as psi bar prime is equal to e power minus I theta of x q psi bar. Now you see only the derivative will play a role exactly in the case as in the case of the scalar case. So d slash is equal to del mu gamma mu. The only thing that's a difference here in del mu, the capital del mu plus ig or ie so the entire idea is exactly the same, meaning the entire structure, everything looks like the same thing. And delta, okay, maybe I'll write it in the next slide. And delta a mu, which is a mu prime, a mu is equal to minus 1 by e dou mu theta. Okay, this is precisely what we have seen for the scalar case. So there's no difference between this as far as this thing is concerned, except that now if you expand LQD, so you have psi bar del mu plus I e q a mu gamma mu psi minus m psi bar psi minus 1 by 4 f mu nu f mu nu. So let's take the first term, so meaning only the kinetic part. So this, if I expand it, I have psi bar del slash psi plus I e q psi bar gamma mu psi a mu minus m psi bar psi minus 1 by 4 f mu nu f mu nu. Now if you look at this term, so compared to the scalar case, which has a second order in perturbation theory, Here you only have one interaction terms. L interaction is only one term. So there is only one L interaction. This rest of this is exactly like the Dirac equation, and the green part is exactly like EM theory. Okay. So you have L interaction. There is only one interaction of the electrons with photons, and that L interaction, okay, exactly like what I said earlier, is always again current interaction. So it is like J mu A mu I A Q. So Q you can absorb in J mu if you want actually. So this J mu is called psi bar gamma mu psi bar gamma mu psi. So this is only one interaction term in electrodynamics, and this is only one interaction term between the electron and photon. That's the only thing. Okay, so far so good. So now so what we need to do now, how do we go further with this? Essentially, let's say um, so how do we compute, say for example, so any simple process or anything. So what we have here is LQD is equal to L Dirac plus L EM theory plus L interaction. Okay, do you all agree with this? So this I know the solutions. Now I treat this as perturbations. Okay, so this is exactly the Q point which we had, if you remember, for any process. So processes in QED, so or in any other quantum field theory, say for example. So what you treat is that you treat the incoming particles as free particles and the outgoing particles as also free particles, and at a very small period of time, extremely small one, there are interactions essentially. Okay, this process exactly at the particular point of this process, and this process which I called was called the vertex. Okay, so this is the vertex. So what I will try to do is try to understand this process, some simple process, and then I'll try to give you the set of rules which try to solve these things. Okay, so let's try to think of some simple process, like say the simplest process you can think of is electron repelling another electron. Okay, now you want to describe this process in QED. This process goes by the name molar scattering. So these are relativistic electrons. So there is an electron at some particular point with some energy and momenta, and there is another particular electron, okay, with a particular point. Okay, now let me say the time is going this way. In the example here, I had time going this way essentially. Okay, out states, these are in states. Okay, so in this particular particles, okay, so what's happening is this is an electron and this is also an electron, EE. So it comes in as a free particle up to this particular point. This point, it radiates a photon. It radiates a photon because I have a photon interaction. I have shown you that it's a current interaction. And this radiation, this photon is sort of seen by the other electron. Okay, it sees this other electron, and the electron sort of absorbs radiation. And you can think in sort of classical ways that this is a radiation. The problem is this could be the other way around. This electron also could radiate and this can go. Okay, so these are your in states. Your interaction happens here and they exchange a virtual photon. This is not a real photon actually. They keep exchanging a lot of photons. That's how they repel. So, but let's just take that they exchange one particular virtual photon and this electron goes away and this electron goes away. So two electrons come close by and so each electron, okay, so they exchange a photon between themselves. Let me call this as exchange. Essentially this could be this way from here and this way from here. That's the reason you don't really put any arrow on virtual particles. Typically on virtual particles you should not put any arrow, especially for gauge bosons actually. Now there are several things we should see actually. So first of all, so this could be some incoming with a P1 and this could be some momentums P2, these things which we have seen. So this could have a spin projection S1, this could have a spin projection X2, and the exchange of this momenta would be around this line essentially. Okay, this could be along this line or this could be along this line. Now let's just say P1 goes back to P3 momenta at the end of the day and P4 at the end of the day. The electron goes back to P3 and this electron goes to a momenta which is P4. Now this is what so I am just drawing this. This is a space-time representation. Okay, this is a space-time representation of the process. Okay. Of the process. The actual process could be quite complicated, but this is the space-time representation of what's happening in perturbation theory, because I am just putting one particular exchange of photon. Okay, I am just putting, this is the interaction term. So this interaction term tells you that this J mu is the current of the electrons, okay, which couples to the photon, with a coupling constant E. Okay. So this is the current, so which comes from present to the future. So this is the current which is going from present to the future. This is another current which is going, electron current, from present to the future. Okay, these two, this current is essentially moving from this to this direction, and this current is moving from this to this direction. And in this process, it is emitting a photon. This is quite possible because it always couples to a photon. And I am just using one perturbation theory, one time one photon actually, and then it just exchanges this one, it goes back to this. So electrons go back to itself. So what we had to figure out is what is the momentum of the virtual photon, because we also need to see how much is the impact, right? So the momentum of the virtual photon, you know, this we had given it. So this is nothing but T is equal to P3 minus P1. Or this is also equivalent to P4 minus P2, purely because you want to conserve momentum. Because you want to conserve momentum, this turns out to be the case. Because this one has started with P1, so the only possibility would be the final state momentum minus. So if it loses energy or if it gains energy through this exchange, so it can be seen essentially. Now the incoming states, I know what these are. I had said what the solutions are, so I can use a wave function for this. And the outgoing states, I can use the wave functions from Dirac equation solutions. Okay, these two wave functions I know. Now similarly, I know the same things here, but I don't know the wave function or the transition amplitude between this point to this point by the exchange of a virtual thing. Because these are real particles, the in and out states are always real, so they can be detected. Whereas the virtual particle is not detected, so you don't see it in the experiment. Okay, so you don't actually see it. What you actually see is only the two electrons coming in and they're repelling and they're going back to some state. Essentially they're coming and going back with some momenta, and they exchange some momenta, and that's it, they go back. So this virtual particle, I don't know, meaning I cannot detect in an experiment. So the only thing I see in an experiment is the initial state electrons and the final state electrons. I don't see the virtual particles or the exchange particles or the intermediate particles. All of them refer to the same thing. Okay. Now, now how do I deal with this? So that is one thing. Now, so this we need to derive this. What do you call? I won't actually derive this, but I will just say what it is. Essentially, that you need to derive uh, the transition amplitude of the exchange of this photon from one point to another, or otherwise is the wave function of the particle, which is the virtual wave of a virtual particle, quote unquote virtual wave function. Not actually a virtual wave function. Okay, it's something. Okay, so but there could be others. It is not just the photons. We also have to derive virtual states for the electrons also. Say for example, imagine scattering scattering of an electron with a photon. So so how do you draw this diagram? So let's just say that again we'll draw with an X. Okay. Okay, so there is an electron coming in and there is a photon coming in. I said the real photon is represented by epsilon mu nu. Because this is an electron, incoming electron, this is represented by a u wave function. So it comes, and then I should get back a photon and an electron. It turns out, okay, now there is no way you can complete this diagram with the Lagrangian unless you exchange an electron, photon, electron. So u could be of spin projection S and momentum P1, and this could be of momentum P2, this could be of momentum P3, this could be of momentum P4. Now if you want to see this, so there is an so why this is the only diagram you can think of. Okay, first of all, the vertex or the interaction is only between two electrons and a photon. Now let's try to put two electrons. So electron, okay. Now, so suppose if I put electron, sorry. So if I draw a diagram exactly like last time, so electron, and a photon, there is no photon coupling in the theory. Such a thing is not allowed. Not there in theory. Okay, such a thing is not allowed. Photon doesn't couple to photons. Okay, so in abelian theories, okay, this is one of the main important rules. In abelian, I'll tell you what I mean by abelian theories. Okay, but just take it out. In U1 theories, we'll come to abelian and non-abelian a bit later when we do the group theories. In abelian theories, the photon does not couple to itself. That means, in other words, you also hear this word a lot actually. It does not have self interactions. Okay, it does not have self interactions. So the photon does not couple to itself. So it doesn't have interactions with itself. It does not have self interactions. Okay, this is an important point that so the photon doesn't have. So this diagram you won't be able to draw it. So this diagram is wrong. So think of any other variations. None of them really work out actually. So the only possible diagram you can have is this one. There is an opposite diagram also, but okay. So again, this is again time in this direction. These are your in states and these are your out states. But now here you see the exchange of an electron. So the exchange of an electron. So this electron is also a virtual. So I have given you two examples. Okay, in one case the photon is a virtual particle. Okay, and this in the other case in which there is a scattering of the electron with a photon. This has some name. It's a very famous name which we have said. Okay, called Compton effect. So this the virtual particle is an electron. So what we need is the transition amplitudes, or what do you call as something called the Green's functions. Okay, or 2-point functions or anything. Okay, there are several names you can think of. Okay, so this should be also there for not just photon but also for the electron. You should be able to derive this. Along the way, what we have seen is that in these theories, it turns out to be the photon doesn't couple to itself, and this turns out to be a general property of all abelian theories. It's a general property of all abelian theories. Okay, so anyway, so coming back to this, so this is, so what we need is essentially the, other than the virtual particle, how do you write the transitional amplitude for virtual particle? So let's do it for the first case, for the simplest case of for a scalar. So virtual particles are, there are several definitions, not on shell. That means they don't really have E square is equal to P square plus M square. They are not physical and not seen in experiments. What you see in the experiments are real particles, okay, which are physical and which are on shell. So these are the properties. Okay, now this yeah, this is some sort of tautology, but anyway, this is how it is essentially, that this is the definition of the virtual particles. So now what we want to do, if there is a virtual scalar particle, So you derive what is it called, um, the transition amplitude between these two points. Let me call this as x and y. Okay, a space time points x and y, and they exchange some uh, a scalar particle. Technically this is given by something called a propagator. Okay, we will know this is a time ordered product of phi x phi y. Okay, you don't have to know all these things, because in a I think in 10-15 minutes I'll tell you that you can just forget all of these things. Okay, and just remember the results actually. So the time ordered product, the vacuum insertion of a time ordered product of phi x phi y. Okay, this is technically the thing. Okay, this is called something called a propagator. The propagator is derived, this is the momentum space representation of the solution of equation of motion. It turns out, actually you can derive it in field theory. In field theory this is what it is. Okay, you can also do it in the classical way actually. In momentum space representation, solution of the equation of motion with a delta function source. Okay, fine. Okay, essentially it means that box plus m square phi is equal to some delta function x minus y, okay, and then you take the momentum space representation of that, try to solve this equation, get the momentum space representation of that, and that turns out to be, okay, minus psi k square by m square. It's actually the inverse of the equation of motion, actually, k square minus m square. Okay, now okay, this is so the derivation of this propagator is slightly complicated. We won't okay, do it. Actually, it's p square plus m square plus something called an I upon. This is called the Klein-Gordon propagator. Okay, fine. Okay, so so this is called the Klein-Gordon propagator. So whenever there is an exchange of a scalar particle between 2 points, it is represented by dotted line and then you know what it is. The amplitude is k square plus m square. There is an I epsilon, okay, in principle, but anyway, let's just forget about this for the present actually. Similarly, if you look at the Dirac propagator or the propagator of a fermion, the same application holds actually. Same the Dirac propagator. So this is given by P slash so this is again exchange of a fermion between 2 points x and y, and then the momentum representation of this would be I P slash minus mf. Okay. Now this you can multiply with the what do you call as P slash plus m on the numerator and the denominator, and this gives me I P slash plus mf by P square minus mf square. Mf is the mass of the mf is equal to mass of the fermion. Okay, now the next step would be for a spin 1 particle, the spin 1 particle being the photon. So if we had 2 points x and y, if the photon is a virtual particle, this has minus I eta mu nu by q square. Okay, there are certain I epsilons and everything here essentially. If this goes with the momentum q square, so this is given by I. Okay, there are other gauge dependent parameters, but I have not mentioned it here. So this is just okay. So for the photon, so this is given for the Dirac propagator. This is represented by a solid line. For a scalar propagator, it's represented by a dotted line. For a photon or for a gauge boson, it is typically represented by a wavy line. Most of the gauge bosons. So you can change the kind of waves you want. Essentially, one could be circular waves or something. Some could be solenoidal waves or something. Okay, it depends upon what we want to. But most of the time, this is just a wavy line. Okay, this is typical notation. Now we sort of have all the ingredients. Okay, we sort of have all the ingredients with which we can ingredients to compute the matrix elements, okay, which were introduced in, I think, in one of the lectures. I don't remember the exact lecture number. In lecture 6 or 7, I don't know. In lecture so and so. Okay, we'll just leave it as it right now. I don't remember the number. Okay, so in lecture number something, we'll fill it up later. So this is so we have all the ingredients. Now all we need to do is how to compute m. Okay, so I made this comment, right, essentially. Okay, how to compute m. the matrix element. Okay, so the first step, okay, all these processes, all which I have done so far, okay, these diagrams, space-time representation or whatever I called it, this is called a Feynman diagram. Okay, these rules, okay, which I am drawing right now, these are called Feynman rules. Okay, so this is using computing M using Feynman diagrams and Feynman rules. Okay, so the first step is, let's consider QCD. Okay, let's consider QED. Sorry, let's consider QED. So the first step would be to consider a process you are interested. Consider the process of interest. So what do you mean by process of interest? So there could be many processes. So for example, the process of interest could be electron-electron scattering. So it's like electron-electron scattering, okay, electron-electron scattering, or electron-muon scattering, say for example, electron-muon scattering. Or whatever, there could be a number of processes like electron-photon scattering going to electron-photon scattering. Okay, electron-photon going to electron-photon, which is given by, this is called the Compton effect, which was in. There could be more nicer process like E plus E minus going to E plus E minus. This is called Bhabha scattering. Okay, then there could be E plus E minus going to gamma gamma. Okay, then there could be gamma gamma going into E plus E minus. So this is called pair annihilation. Okay, this is called pair creation. This is called Bhabha scattering. Okay, this is Compton effect. This is Molar effect, Molar scattering. Okay, so these are the typical sample process in QED which are important. There are more complicated processes like Delbruck scattering, like gamma gamma going to gamma gamma, which are higher order in perturbation theory. Okay, so what we have is we have only a theory of just electrons and so we'll forget about the scalars for the present. So and what we have is a theory of just electrons and photons. It's a very simple theory. It is just a U1 gauge theory, and it conserves charge at every particular space-time point. So we'll just see that how it does. Okay. So let's consider. So what I have is, so we'll just write a set of rules collecting all the information we had about from all this background and whatever little bit quantum field theory I covered. So all that information and everything, using that, okay, I can sort of so what do you call, as collect all the possible set of information which I can have, and then I'll say that I can write an amplitude in a particular fashion. Essentially, I can write an amplitude for the, or M, the matrix element, which is the amplitude for the so what of a given process. So the first thing is to select the process you're interested in. So write down, so the first step. So now what we are going to do is essentially something called the algorithm for computing um, process in QD. So there could be any number of whatever simple process. So the first step would be to select a process of interest, meaning think of the process of interest. Focus on the process of interest. The second step is draw all possible Feynman diagrams okay for the process of interest. Okay, now the second step looks a bit tricky. It looks like okay, meaning you came to say, so how are we sure that we are not missing some diagrams or something? Yes, that's a good question actually. uh, it could be non-trivial in complicated cases. For QED, most likely you have you don't really have such a you don't really hope that you will miss diagrams in at least in lower in perturbation theory, in the first order in perturbation theory. Okay, so I'll try to give you some examples. Let's consider, say for example, the first step is to consider process, like for example, so let's try to draw all process say for example, let's take molar scattering. Okay, let's start with molar scattering. Now before doing that, you remember that I talked about so if you have any given 2 to 2 process, say for example with momentum P1, okay, P2, P3, P4, you have only 3 possible exchanges which you can have of the momenta exchange within this blob, essentially within this thing which has the interaction part. Okay, this could be higher order or lower order in perturbation. What will be the order in perturbation theory? Okay, so you can only have 3 possible things. So one is P1 plus P2 whole square, which I call it as S. The other is P3 minus P1 whole square is equal to P4 minus P2 whole square, that is equal to T. And the third one is P4 minus P1 whole square is equal to P3 minus P2 whole square, that is equal to U. So as long as you are in at the tree level, say for example, and then also you are in 2 to 2 process, you know how to organize all the possible diagrams. So you ask whether you consider S channel. If S channel is possible, okay. If it's not possible, is T channel possible? Okay. If it is possible, is U channel is also possible? That's the only thing you can think. So this all the 3 channels could be possible in a given process. Okay. So one can okay, there is something called exchange symmetry and everything. But anyway, so all the 3 channels could be possible. So you look at all possible diagrams which can be possible for a given process. Okay, I'll explain what you mean. So let's consider the case of molar scattering. So the molar scattering is electron acting at an electron. So electron comes, exchanges a photon, and then goes back. So another sees another electron, both of them exchange a photon and go back. It's simple. Now let's consider, is there any vertex, say for example, so this is the time direction is this one. Now, so to draw this, I'll try to summarize what is the thing which we can have. Okay, let's try to draw and then I'll write down the Feynman rules. Okay, so let's try to draw this. So for example, let's say that this is the time direction. Okay, so that this helps us for thinking actually. So this is the time direction. So let's say an electron comes and an electron comes, both these electrons. The question is, can they meet at one particular point? Okay, let's just say they meet at one particular point. So then I can have P1 and P2 sum over. So there could be something called an S channel process. Okay, let's see if this is a possibility. Okay, let's do that. So let me just say that both of them are electrons, and they give you a photon. That's the point. So this is electron, this electron. Now, is such a thing valid by the theory? No, it turns out that this is not valid by the theory. Why? At this vertex is not possible in the theory, because at this vertex electric charge is not conserved. Why? Because electric charge is coming like this. So it's an incoming particle and this is also an incoming particle. This carries a charge -1, this carries a charge -1. Both the charges add up at this vertex, and the photon doesn't have any charge. The photon charge is 0. This is charge q is equal to -1. This is charge q is equal to -1. It comes here and charges. So if this is true, if this S channel is true, if this X channel diagram exists, the vertex, the photon should carry a electric charge of -2, but which doesn't happen. So the theory, the Lagrangian does not allow this kind of diagrams actually. It turns out that the Lagrangian doesn't allow these diagrams. So the S channel, if you want, you can also see that because electric charge is conserved in the Lagrangian, these diagrams are not allowed. So there is no S channel in the process of E minus E minus going to E minus E minus. Okay, this will be clear when you see the Feynman rules. Okay, but let's argue why this is not true, why this is not valid actually. Okay, so even if you want to draw, go ahead and draw, you'll be violating. So if you just say that, okay, I don't care about everything, so I'll just keep drawing this thing, but then you'll hit up a problem that you are violating electric charge. Electric charge, and so also gauge invariance. So S channel is not possible. So even if you want to follow, okay, I know this process, I don't really care where the Lagrangian is and everything, I don't really care what the Feynman rules are. So if you want to draw like this, okay, you'll end up with a soup. So S channel is not possible. Very good. Okay, what about T channel? Okay, T channel would require an electron going into electron. This is the diagram which we saw, and another electron going into another its electron. So this is P1, this is P2, this is P3, this is P4, and then you have a photon with a momentum q, a virtual photon which is exchanged. Okay, so this is time in this direction. This is the same diagram we had considered earlier. Now this photon can have, so you can have a more q is equal to P3 minus P1. Okay, this is possible. So T channel diagram is allowed. Now, is this the only diagram you have? Is there any other diagram? Now you know how many, because it's a 2 to 2 process. There are 3 possible exchanges. Okay, you can ask the question whether this P1 can interact with the momentum P4. Okay, so that means this electron goes there with P4. So you can exchange P3 and P4. So yes, that is possible. So you can have a U channel So P, okay, electron, okay, this is another this thing, again P1, P2, P4, P3, okay, Q, and Q is now P4 minus P1 whole square instead of P3 minus P4. Okay, so essentially I drew I just exchanged P3 and P4. So instead of having P2 P3 minus P1, this exchange is between P4 and P1. So I represented it this in this particular fashion, in the diagram in this particular fashion. So with this I have got all possible diagrams. Now I am sure, so at the lowest order in perturbation theory, I have got all the possible diagram. This is easier because this is a 2 to 2 process actually. It's like E minus E minus going to E minus E minus. So which is nice actually, but anyway, but this is an extremely useful trick to use directly the Feynman rules and Feynman diagrams actually. Okay, so this with this I know now I have for the molar scattering there is only T and U channels. So this means with this I have all possible diagrams, Feynman diagrams. I have drawn all possible Feynman diagrams required or representing, okay, representing the molar scattering. So we have covered the first step. Okay, so now after this, okay, let me stop here. I don't know. Okay, and then in the next part we'll see how to compute starting from the diagram, how do you compute the rest of the things, and then we'll see more and more examples.